Well, hello there, and welcome to Pandemic Radio, Epidemiology 101 edition. On today's always exciting episode on the COVID 19 pandemic using planetary health perspectives, I wanted to give you all a quick rundown on some of the epidemiology of the pandemic. We are all, as in we, I mean, humanity, getting a crash course in epidemiology, whether we know it or not, and whether we like it or not. So, this is just kind of a grab bag of different epidemiological uh, tools, techniques, etc. Um, and some of you may have seen some of this before if you've been in such wonderful classes as epidemiology with Dr. Bales. Um, or most of you have probably seen a lot of this stuff just from kind of living through a pandemic. So let's start with one of the fundamental goals or duties or kind of MOs of an epidemiologist. So basically, we are all about putting numbers to diseases. We want to count uh, diseases so that we can understand patterns of spread, um, geographic clustering, who's getting sick more than others, etc. And to do that, we need a way of measuring the amount of disease, and in this case, the amount of COVID 19 uh, spreading around the world. So we are counting, get it? All right. Sesame Street fans out there? Uh, Disease in a number of ways. And what I think is interesting about this pandemic is all of the cool these are called dashboards that a lot of you guys have probably seen. There are a lot of them, and this one is probably the most famous. It's the most widely used, and it was one of the first. The coronavirus dashboard that is uh, put together and monitored and maintained by Johns Hopkins University. And essentially, what it is a way of visualizing and tracking epidemiology statistics, the different ways that epidemiologists measure disease. And essentially, what we're looking at here is descriptive epidemiology in a nice little, easy to understand package. So again, this is a fundamental uh, part of the epidemiological approach. It's like Epi 101. And the first step is to find some kind of disease pattern, right? We count up the amount of disease, we count up cases, and then we look for trends, we look for patterns. In this case, it's a map of diabetes in the United States, and we can say, well, the pattern here appears to be that diabetes is more intense in the southern portion of the United States along the Mississippi Delta. And the next logical step is to ask, well, why is that? Why is diabetes higher in some areas and lower in others? There's some reason for why disease looks the way it does in a population. Disease seldom is just kind of random. Usually there's some thing or things causing disease to look the way that it does. Sometimes it's in a map, sometimes it's comparing groups of people, sometimes it's looking at trends in disease over time. Uh, and then the last kind of major step is, trying to figure out what could be causing those patterns. So in this case, this is a map of obesity in the United States. And if you look at the two patterns, you see some strong similarity or correlation there. And this is kind of just like epidemiology. So there you have it. So there are a lot of different ways that epidemiologists can count and measure the amount of disease. And I'm not going to go through all of them. I'm just going to touch on a few that are widely used to track the COVID-19 pandemic. And I just realized something that this little cartoon has a lot of bat imagery in it. And if you guys enjoyed and remembered my origins of COVID-19 uh, lecture, hopefully you're getting a nice little chuckle right now. So, we need to count disease, and in order to do so, we need to uh, basically define who gets counted and who doesn't, who is a case and who isn't, who gets counted and put in one of those dashboards as a COVID-19 case, and who maybe just has the flu or something else, maybe that is kind of similar looking but not caused by the virus. So, epidemiologists put together what is called a case definition, which is basically just a series of criteria. Think of like a kind of a bunch of check boxes. You need to like go through this list and say, okay, do you have these symptoms? Do you were you in this place at this time? It's basically just a set of criteria that you use to ascertain whether someone should be counted or not. And usually, when you're dealing with an outbreak such as COVID-19, um, your early case definition is very, very broad, at least compared to later definitions. And this is because early on in the outbreak, you are trying to uh, cast a wide net, and you don't want to miss anyone if your definition is too narrow. Like if you have too many boxes that need to be checked and it's too specific, you might miss some people. So case definitions evolve from usually more broad and simple definitions early on to more specific, usually over the course of the outbreak because we learn more about it. For example, at the very beginning of the COVID-19 pandemic, we didn't have a name for it. We didn't have a name for the virus. We just knew that it was a cluster of um, people with a similar kind of strange respiratory illness. So now that we have our set of criteria, we need to be able to like go out and actually like identify people who fit this criteria and count them. This is Mr. Dustin Hoffman from the movie Outbreak. And usually we are, at least in the early phases, counting the quote unquote tip of the iceberg. We are able to count and identify people who are usually just very obviously sick or very obviously fit the case definition. There are, as we've learned with the COVID-19 pandemic, a lot of people who are asymptomatic, who do not have the clinical symptoms that would classify them as a case. Uh, some people might have very mild illness and never seek medical attention. Um, we can only essentially count the cases that we can see, uh, at least early on, until we start doing more sophisticated kind of testing. And I think we'll get into that later in the class. So, usually at the beginning of an outbreak, we are just kind of scratching the surface. And a lot of the numbers and statistics that come out represent just a fraction of the overall total number of true cases. And when we're dealing with public health and when we're dealing with disease surveillance, it's very, very difficult, if not impossible, to get an accurate, full, complete picture of the total number of cases of disease. I'm quite confident that we will never know the total number of cases of COVID 19. It's just not feasible to count every single case. So we try to see as much of the iceberg as we can, but we know that it's an imperfect system. So the simplest way of doing this, of counting uh, and measuring disease, is literally just adding up the number of people who fit the case definition and who are counted as a case. So this is helpful, obviously, for a number of reasons, but it can also be a little misleading. Uh, I notice this as probably one of the top things that are confused by the general public when talking about the COVID 19 pandemic. So here's the example that I use. Um, let's say we wanted to measure the influenza season in 2016. So we compare the number of cases that were counted in San Francisco and the number of cases that were counted in San Rafael. And if you look at just the number of cases, you would say, well, San Francisco got hit way harder. There's like a lot more cases there. What this fails to take into account is the population of each of those places is very, very different. So when you're dealing with an infectious disease outbreak, it's just a natural product of the fact that there are more people. You're probably going to end up getting just more cases because there's just more people. Uh, so if you just look at the raw case numbers, you're essentially, in a way, measuring also the size of the population. So it's not really a fair comparison to say, well, San Francisco has a way worse flu season, but it's just a higher number in part because their population is a lot bigger. So epidemiologists have a clever way of getting around this. We essentially control for the differences in population by taking the incidence rate. All you have to do is divide the number of cases by the population, and these numbers, for example, 0.0078 and 0.0603, those are both the incidence of influenza in the respective cities. Um, this is the number that you should compare because it uh, is controlling for differences in the size of population. And usually you see it standardized with something like per 100,000 or per 1,000 or per 1 million. Basically, all you have to do is just take that incidence rate and multiply it by 100,000 in this case. So that gives you a nice round number to compare. So the incidence rate of influenza in San Francisco was 780 per 100,000, compared to San Rafael, which was over 6,000 per 100,000 people. This shows you that actually the risk of flu was much, much higher in San Rafael because we controlled for the size differences in the population. So let's look at COVID 19 as an example. I actually just heard this today from some people I overheard talking. And as one does, you inevitably get into conversations about COVID um, when you're out, going to the grocery store or something. So, what I overheard was, oh, well, California is leading the country in like incidents or cases or COVID. Um, and you often see these kind of rankings, these kind of statistical data sets put together and ranked according to the number of like total cases of COVID. So in this list, you see that New York has over 400,000 cases, California has over 400,000, and on down the list. Um, this is just the raw number of cases, the number of people who have been classified as a uh, COVID case. And it is, again, misleading because, as we know, these states have very different sized populations. So if you sort this same list by, in this case, the number of cases per 1 million, uh, this is just like the last example with the flu in San Rafael, except instead of multiplying the rate by 100,000, they've just multiplied it by a million. Same idea though. This gives you an idea of the risk of COVID uh, for the different states. And if you order them by this incidence rate, you see New York is still at the top, but in this case, California drops off the map and ends up being somewhere around the middle. So, this is an example of one of the tools that epidemiologists use to measure disease. What we just walked through was an example of incidence. And incidence is the number of new health events, the number of new COVID cases, for example, in a defined population, like California, for example, within a specific time period. So it can be, you can calculate the incidence uh, yesterday, within the last week, month. You define the time period and you just divide the number of uh, disease events by the population. There's our handy dandy equation. Um, Not super difficult math, but very useful statistic and used often. So, again, new cases divided by people at risk. Okay. So, if you're trying to calculate incidence rate for COVID in California over the last week, you would not include someone who was diagnosed a month and a half ago. Okay, just the number of new cases that occur during your selected or given time period. And this is used as a good measure of risk for allowing us to make comparisons, um, comparing risk by controlling for the different size populations. So again, an example of how this is used. What is the risk of whooping cough or pertussis in the United States in 2013? How would you calculate this? Well, you take the number of cases that were diagnosed and you take the size of the population. You do a little mathematics. If you want to multiply it by 100,000, here's what it would look like. That is your risk of whooping cough. That is your incidence rate, 9.1 per 100,000. Sometimes you will see this get confused with a similar disease measure statistic, which is disease prevalence. This is different from incidence because whereas incidence gives you the number of new cases of disease in a given population, prevalence gives you a calculation that is based on the total number of cases divided by the population. So, regardless of whether someone was diagnosed with COVID last week or last month, if you're looking for the prevalence of COVID um, in a location, you would include everyone who is sick during that time period. And here's how I keep those two straight, because I remember when I was first learning epidemiology way back when, I I was always having trouble, I guess, keeping the two straight. Like, which one's incidence, which one's prevalence. Um, what do they tell me? And I always just think of a bathtub, but not this bathtub. This bathtub, the epi bathtub. Rub a dub dub, the epi bathtub. Incidence and prevalence are two ways of describing the amount of disease, or in this case, water, in the tub. Incidence, in this example, is the amount of new water entering the tub. Drip, drip, drip. The higher the incidence in an area, the quicker the bathtub is going to fill up. Prevalence is the amount of disease in the population. Your population is the tub, and the prevalence is the amount of disease. Whether that water got added 5 minutes ago or 5 days ago, it is counted. One way for disease to change, the water levels to change in a bathtub, is when people die, they have left the population. So when mortality rates are very high, that can affect the prevalence of disease. Or if people are recovering quickly, that can also affect the size of the water. Mortality rate is something we also see quite commonly when looking at COVID-19. Mortality rate is just like incidence rate, except instead of the number of new cases of disease, we are measuring the number of deaths in a given time period. So it is deaths divided by the population size, and then that gives you some idea of the risk of death. And we can take this calculation and we can apply it to different groups, and this allows us to look for patterns. So, something that was seen early on in the COVID-19 pandemic was this pattern of age being a significant kind of risk factor. So, we compared mortality rates between these different age groups, and you can see that age appears to really increase the risk of death um, in this case. If age had nothing to do with mortality risk, this would probably just look like a flat line, or just kind of like up and down and all over the place. But very clearly, age and mortality rate appear to go together. Case fatality is another statistic that we commonly see. This is a good measure of how severe a disease is because it is the percentage of people that have COVID, for example, and who will die from COVID. So essentially, if 100 people get COVID-19 and 10 of them die, you have a 10% case fatality. And we can compare different diseases using case fatality rates, and that's often used to compare like how kind of serious or scary a disease is. You see that seasonal flu is typically around 0.1%, so quite low compared to diseases like SARS, which is a relative of COVID-19. That was at 9.6. Strains of avian influenza or bird flu can be 60%. Some Ebola outbreaks have been higher than 90%. Um, and you can see that our understanding of the fatality rates for COVID has been changing. Uh, so there's a lot of talk about comparing mortality rates with COVID-19 to seasonal flu. And there's also a lot of speculation about what the actual mortality rate of COVID really is. So that estimate goes up and down and fluctuates. But if mortality rate is calculated by taking the number of people who die from a disease divided by the number of people who were diagnosed with the disease, uh, that that statistic can be misleading or inaccurate if if you think back to the iceberg example. We're only counting what we can see or the tip of the iceberg. If we're not diagnosing a lot of the cases, that's going to give us a biased estimate about the true mortality. So let's say we diagnose 100 people with COVID 19 and 10 of them die. Uh, that gives us a 10% uh, case fatality rate. But let's say in reality, 1,000 people had COVID 19, but we were only able to identify and count 100 of them. We're still dividing 10 by, in this case, 1,000. So that gives us a much smaller mortality rate. And if we want to see an example of just kind of how these indicators of mortality are used side by side, we can compare its use in this example. Let's say this county has 20,000 people. Uh, 30 of these people were diagnosed with Lyme disease, and two died from the disease. So the mortality rate is calculated as 2 divided by the size of the population, and we multiply it by 100,000 to give us a mortality rate of 10 per 100,000. The case fatality rate is, again, the number of people who die divided by the number of people who were diagnosed with the disease. In this case, 6.7%. Okay. So two different statistics telling us different aspects of the severity of the disease. So what we've essentially been doing is describing the tools for producing what's called descriptive epidemiology. So person, place, and time. We want to be able to put these statistics on a map and look for where hotspots are emerging, what parts of the country are experiencing higher rates of COVID than others. When I showed you that figure showing that mortality rates increase with age, that is an example of descriptive epidemiology. So we're looking for these patterns to be able to describe the disease, and then, ultimately trying to figure out why. Why do older people have more serious health outcomes? Why do people with certain pre-existing conditions have higher mortality rates? Um, it's recently been shown that people who smoke cigarettes or even vape have higher mortality rates than those who don't. Um, but the Why Though family portrait, um, something kind of horrifying about, but it makes me think of the different ways we can describe the distribution of disease in a community. So again, what you will often see in these COVID dashboards that I showed earlier is essentially just a visualization of basic descriptive epidemiology. So COVID-19 by person, so comparing like age, gender, race, uh, comparing place, country, state, city, and time. So looking at how the disease is changing over time. And how the disease is changing over time is a incredibly important aspect of descriptive epidemiology, especially when it comes to an infectious disease outbreak and pandemic like our uh, our enemy COVID-19. So what we see constantly and what people have been bombarded with in the last several months is what's known as an epidemic curve, or epi curve, as I like to say. And essentially, what this is just a simple graph of the number of cases plotted over time. And it looks something like this. So if you see on the x-axis, you have time, okay? And on the y-axis, you see just the number of cases. So essentially, what this is just a histogram, but it tells you a lot about what's going on. You can look at how the disease is changing over time. Is it increasing? Is it decreasing? What's happening? Are there outliers? uh can you look for like weird spikes or weird kind of differences when you look at comparing epidemic curves with different locations? um how big is the curve, right? So is it a little blip? Does it kind of not go up that much, or does it start spiking really high? Um and this gives you an idea too of when when the outbreak was likely started, um, and if intervention and control measures like the whole shelter in place stuff are working. We can also get a good sense of the disease's incubation period. So this for COVID would be the time between when you are infected with the virus, and you first start showing symptoms. So if you are um, infected, the virus, let's say you inhale it, it begins an infection, and you start getting your first symptoms 5 days later, maybe like a headache and a fever. Um, the incubation period for you is 5 days. And if you kind of average up everyone's incubation periods, that gives you the incubation period for the disease. And incubation periods are kind of like the fingerprints of the, you know, pathogen. So different viruses and bacteria have different incubation periods. Some of them are very short, some of them are just less than a day or a few days, and some of them can be very, very long. Uh, the epidemic curve allows us to kind of visualize this in a pretty easy way. So the incubation period for COVID-19 is thought to be usually 4 to 5 days, um, and could be up to a couple weeks. Uh, that's why you see when someone is suspected to be exposed or test positive, they have to self isolate for 2 weeks. It is because that is the um, kind of tail end of the incubation period. So studies have shown that about 97.5% of people with COVID-19 who are going to develop symptoms within 11 and a half days. So basically, the 2 week window is like um, a good way of capturing most of the people who are going to get sick. So if you're exposed to COVID, and you're gonna get sick. Whether or not you get sick, you're gonna know basically within 2 weeks. Uh, 4 to 5 days means that about half the people who are gonna get sick from COVID get sick in about 4 or 5 days. So the incubation period, the median incubation period, is essentially just looking at the when people are exposed to the pathogen, and then just following that to the middle of the epidemic curve. And you probably have seen epidemic curves before, even if you didn't know that that's what it was called. These are epidemic curves, or epi curves. Um, and it again shows you about the magnitude. So how tall is the curve in different locations? It shows you, a lot is made about the shape. How fast is it increasing? How steep is it? Is it going up and then down and then up again? You can stack multiple curves together, like the graph on the right shows the United States and the European Union. These are epidemic curves that allow you to compare what's going on with the disease in the US and what's going on in Europe. And you see two pretty different stories currently, but both locations had similar kind of rapid spikes in the number of cases. Um, you can also start to tell a story. So in the US, you can see that a lot of the social distancing measures and a lot of the kind of shelter in place orders that were put in place started to have an impact and started to bring the curve down. And then you've seen what we're dealing with now is as these restrictions were lifted, the curve is bounced back and going back up. So the epidemic curve tells you a lot about kind of the scope and nature of the outbreak. So usually you see with an epidemic curve a kind of bell-shaped curve if the uh, source of the exposure is kind of short. If there's like a short window of time that people are exposed to the pathogen and then it goes away, you're going to see a curve like this. So, like if the salad bar at the store, the grocery store, was contaminated and then it got cleaned after a day. So only one day went by for people to get exposed. This is what the curve would look like. When people are kind of continuously exposed to whatever's making them sick, you see basically an epi curve that like doesn't go down because people are continuing to get exposed over time. And it can also look something like this, where it kind of goes up and down and up and down. And this is sort of the case with COVID in that there isn't just one single source of infection. It's not just like one person, uh, standing on a street corner coughing at people, and that's the only way people get exposed to COVID. It's passed person to person. So there are many different, kind of mini beginnings of the outbreak. So again, the this is the epidemic curve for the uh, COVID-19 pandemic from the beginning. So you see the first cases start to kind of trickle in January. You see the first spike. This is in the Western Pacific in China. And right past February 10th, you notice that big spike in orange. Um, that would be an example of like an outlier. So that would be um, worth investigating. So did the amount of disease really just spike that much? Or maybe we started counting cases a little differently around that time. And it ended up being that that's what that was. The case definition ended up going from narrow to a little wider, and it started capturing more people. So more people just ended up getting counted as cases. So this is an example of surveillance bias when it's not the actual uh, risk of disease that's increasing, it's how we're counting the disease that is changing the pattern. And I am going to pick it up on part 2. So I hope to see you back same time, same place. Well, I guess it's YouTube, so you can watch it whenever you want. But we'll be back for part 2, and we're gonna wrap up surveillance bias and get to that. Here's a little sneak peek: the flatten the curve business. What's up with the flatten the curve? Well, we're gonna get into it. So come back for part 2.